So now that we've talked about what volatile is conceptually, let's take a look at an example to illustrate how it can be used. And this is actually a pretty cool example. So as we talked about before, volatile is a relatively simple and efficient way to ensure that reads and writes of fields occur atomically with all the good side effects like visibility is handled, ordering is handled, consistency is handled, and so on and so forth. And to take a look at how you can use volatile, we'll see how it can be used to implement something called the double-checked locking optimization pattern. And this pattern, you can read about this pattern at Wikipedia. I was actually the author of this pattern about 23 years ago or so, and it was pretty cool. I discovered this when I was working on my PhD dissertation, which is about 26 years ago, and discovered on the multiprocessor platform I was running, I was seeing some weird problems when I was using the singleton pattern from the Gang of Four book. Things were behaving inconsistently. I was like, what is going on? And in looking into this further, I realized that there were some flaws with the singleton pattern in the Gang of Four book. And so I documented this pattern called the double-checked locking optimization pattern as a way to overcome those limitations. And as it turns out, that's a cool pattern based on certain assumptions of reading and writing to memory with what's called strongly ordered memory semantics. But if you're on a modern or a more modern platform that didn't have strongly ordered memory semantics but had weakly ordered memory semantics, then the singleton pattern doesn't work, and the double-checked locking optimization pattern doesn't work either, unless you take steps to avoid that. So it turned out that this particular issue was a problem with the Java memory model, and so there was a firestorm of discussion over several years, and if you read this website, you'll find out more about that. And they finally, in Java 5, which came out in 2004, fixed this problem with double-checked locking. And the way they fixed it was by enhancing the semantics of the volatile keyword. So we'll kind of talk about that. Here's basically what the pattern says to do. It says, the double-check locking optimization pattern says, the first time you come in to check to see whether a singleton has been created yet or not, you check to see if the current value of the singleton is null. And if it's not null, that means it's already been initialized, in which case you just go ahead and return the result. But if it is null, you go ahead and synchronize on some single lock, like the class object that's part of every Java object. And then you go ahead and create the single instance. So that's basically the idea behind the pattern. You only initialize the first time in, and you do a double check. So you first check to see if it's null. If it is null, you grab the lock. Then you check again to see if it's null. And if it's still null, you go ahead and allocate the object. And this is what's called essentially lazy initialization, or what's also sometimes known as a first-time in check. And the problem here is before they added these enhancements to Java 5, you could end up with inconsistencies because the semantics of the Java virtual machine didn't guarantee certain properties. So what they did is they updated the behavior of volatile to ensure just the right amount of synchronization in a Goldilocks and the Three Bears-like model. And so by defining this thing as synchronized, it means that we only need to synchronize when the static volatile singleton is null the first time in. And all the other subsequent times, it'll work properly, and the write here to here, this one, sinst equals result equals new singleton, that operation will guarantee to propagate through to all the other places that are accessing sinst, and therefore any other calls that come through will be guaranteed to work properly. So there's no need to synchronize after sinst is initialized the first time, which is down in here. But remember, singleton, the volatile rather, is limited to a single read or write operation. So there's a single read operation. We read from the static volatile sinst. That's done atomically. And there's a volatile write operation. We will basically assign to sinst as writing result into sinst. And all that is done atomically, and it propagates correctly through the memory hierarchy so that you have strong memory guarantees. So that's a really cool example. And again, if you want to learn more of the history of this, you can go back and take a look at that website. And it was a great example also, in my mind, of how documenting software idioms in terms of patterns helps to make it more clear what the intended semantics are, so that people can then improve their runtime environments to give you consistent and dependable results, which is really what happened in that environment.